Hey everyone, and welcome back to our Python data analytics series. In the last episode, we went over data visualization. In this episode, we're going to go over some common analysis functions and explore the idea of correlation. So this will involve getting things like mean, median, and standard deviation, as well as finding correlations between two variables. So the first thing I actually want to do is quickly do a review of some stats terms so we're all on the same page here, since we'll be using functions to find these terms very shortly. This isn't a stats course, so I'm not going to go over these terms incredibly in depth, but we should all at least know what they are. So the first term is mean, which just means average. A mean is acquired by taking a set of numbers, adding them all up, and then dividing them by the total number of numbers that there were, and then that gives you the mean there. So if we had this list here, we add them all up, this list here, we add them all up, we get 350. There were 5 total numbers, we divide it by 5, we get 70, so 70 is our mean. So next we'll look at the median. So median is just the middle number in a set of numbers when they're sorted in order. So let's say we have 5 numbers. We have 40, 10, 28, 7, and 85. So to find the median, we first need to sort the numbers. So we'll just write them as 7, 10, 28, 40, and 85. And then if we look at the middle entry in this series, it is 28. If we, for instance, were to take out the 28 and we had a set of even numbers, then the median would just be the mean of the two middle entries. So in this case, it would be the mean between 10 and 40, which would just be 25 in this case. Next, we'll look at the variance. The variance is the mean squared difference of each data point measured by the mean. What this means is that we find the mean, then we find the difference of each value in the data set from the mean, square it, and then add all these together and then find the mean of these numbers. If that sounds kind of confusing, let's look at a really simple example. Let's say we have the numbers 2, 3, 7, 9, and 12. So we first need to find the mean of these numbers. So to do that, we're going to add all these numbers up, which gives us 33, and then we divide it by 5 total numbers, which gives us a mean value of 6.6. And then for all numbers in our list, we need to find how far away each number is from the mean and then square it. So to do this, we can just use subtraction. So the very first number we have on our list here is 2. So let's just show an example of how we'd find the square difference of this number. So we would take 2 minus the mean that we calculated, which is 6.6. And then this should come out to be, I believe, negative 4.6. And then we square it, which becomes 21.16. And then we would repeat this process for every single entry. So we do the same thing for 3, 7, 9, and then 12. And so that's why you see these numbers here. We have 12.96 for 3, 0.16 for 7, 5.76 for 9, and 29.16 for 12. Then we just want to add them all together and divide them by 5 total entries, which gives us 13.84, meaning our variance is 13.84. So variance squares the differences to avoid negative numbers and just gets absolute value differences. However, this should be noted when we look at our final variance value of 13.84. This value is the mean of all the squared differences. So if we want to get our variance number back down to normal units instead of squared units, we should take the square root of that. If we take the square root of 13.84, we get 3.72. But guess what? Now we've just found our standard deviation, because standard deviation is just the square root of variance. So our variance is 13.84, and our standard deviation is just the square root of that, which is just 3.72. So standard deviation is basically just measuring the average deviation from the mean that each value has. So basically, it is measuring how dispersed and varied the values actually are. So hopefully now, after that really quick review, you should have a refresher or base knowledge of what all these statistical terms actually mean. So let's actually apply them to the dataset we've been working with to get started with our statistical analysis. Now, Pandas actually has super easy functions for every one of these terms we just went over, meaning we don't have to sit here forever with our calculators trying to figure out what these terms mean. Pandas can do it in one line for us. So let's take mean, for example. Assuming we have our AI dataset loaded in, let's call this mean function. It's literally just as easy as typing mean. So I will type dataset.mean like this as a function. And then if I were to run this code block, you'll see that it prints off the mean value for every single variable in the table. This mean function treats each numerical column as a set of numbers and then performs mean calculations on every single one of them. So after summing up all the talent numbers in our dataset and dividing them by the number of entries, the mean is 16.803, for instance, as we see right here in the table. Doing the same for infrastructure, we can see that the mean is 63.5. This mean function is basically called on the whole data set and will print out this really nice, simple tabular format for each variable, which could help tremendously in your overall analysis. So if you actually notice here, we're getting a little warning that says, there's a numeric only thing here. And if you read it, basically what it's saying is that it's giving us a problem because we're selecting the entire data set, which is technically an issue because we have columns that are non-numerical, like income group, that don't have numbers in them. So to silence this warning or just to select whatever columns you want, we can use lock or ilock functions from the data selection episode to select specific columns to take the mean of. So what I mean by that is doing something like this. Let's use our log function to actually just select all the numerical columns we have. So I'm going to use colon for the rows to select every single row. Then I'm going to select only the numerical columns, which is everything from talent all the way through total score. And then now if we run this code, it prints off the same exact thing as before, except the wording is removed since we're specifying the exact columns we want to look at, which are just numerical. And of course, as with anything else with our selection, we could narrow it down if we wanted to. Let's say we only wanted to grab all the columns from, let's say, talent to research. We could just replace it like that, print it off, and then it only grabs the mean for these 4 columns. So talent, infrastructure, operating environment, and research. And as usual with lock, we can do really any selection we want. But of course, we wouldn't need to use lock if we wanted to just select like columns individually by hand, whether we just grab like 1 or more. So if we want to look at the mean of like just talent and total score, we could actually just remove the lock here. And then what we could do is just remove this colon here. And then we could do something like this, except we would need double square brackets here because it's technically a list inside of this. And then if we did it like this, we would just be selecting the talent and research columns without actually having to use the lock function. So if we were to run this, you see it only prints off the mean for talent and research. And of course, if we wanted to, we could just select more columns. Like obviously, we can just put it like total score or something like that here, and it would have the mean of total score as well. And lastly, we could just grab the mean of 1 column if we wanted to. So I could just remove this list here, and I could literally just pass in a string of a single column like that and say, what is the mean of the talent column? We print it off, it is 16.803. So just a minute ago, we went over these other terms besides mean, like median, variance, and standard deviation. And one of the great things about Pandas is that every single one of these terms has a super easy function to grab them to. So let's get new code chunks for each one, which I have down here. So to grab the median of the whole data set, we can just type dataset.median like this, and then it will give us the median value of every column in the data set. If we wanted to grab the variance of the entire data set, we could say dataset.var like this, and it will give us the variance of every single column. And then to grab the standard deviation of all the entire data set and all the columns, we could do dataset.std like that, run it, and this gives us the standard deviation of all the columns. So just so we're all on the same page, let's go up to median real quick, which we just calculated. And just like we went over with the sample data, this function will look at every column and find the middle value when they are sorted properly. So the middle value or median for, let's say, the development column is equal to 9.005. And this is the same case for obviously every other column. We sort them in order, look at the middle entry, and then we can calculate the median for every single one of these columns. And the same selection rules are going to apply with median. Like for instance, if we wanted to grab the, let's say the research column's median, obviously we could just type in research like this, and it will give us just the median of the research column. And then if we look at the variance here, we need to calculate the mean of the squared differences of every value from the mean of each column. So in doing that on an entire data set by hand would take forever. So luckily Pandas does it all for us. So for example, the average squared difference or variance of every value in the government strategy column is equal to 689.19. And then we know the standard deviation is just the square root of variance. So for example, 15.21 standard deviation for talent is just the square root of this 231.49 number up here. And the same applies for each one of the values on this list as well. They're all just square roots of their corresponding variance numbers. So just so we can get a little bit more comfortable with the idea of selection using these functions, let's actually just go up here to our median. And let's say I want to find the median of all columns between talent and development. So to do that, I could do something like this. I could say .lock. I would select every single row, and then we want to select every column all the way from talent all the way to development, and then run it. And I would get the median of these 5 columns. Next, let's say I'm looking for the variance of the columns talent, research, and total score. We could do it something like this. I could do double brackets here, and I could just pass it in as a list. I can say talent, research, and then total score like that. And then if we run it, it would print off just the variance of these 3 columns. Lastly, let's just say I want to find the standard deviation of just the government strategy column. To do that, I could just do a simple square bracket here. I could type government strategy like this, .std. If I run it, it will give me the number of standard deviation for the government strategy. So basically the idea that I'm kind of getting at here is that you can use any of these mean, median, variance, or std functions with any possible selection of data. This can be a super helpful part of statistical analysis as mean, median, variance, and standard deviation are 4 super common measurements of data sets. So the last thing I want to do in this kind of shorter episode is look at something that is super common for data analysts to actually explore, and that's the idea of correlation. One of the most common things data analysts or data scientists do is explore the data to see if one variable strongly affects another. are basically seeing the relationship or correlation between two or more variables. One way to check correlation would be to make individual plots in the same way that we did in the data visualization episode, using something like scatterplots. So when we did this, we just used material plotting library to plot two individual columns from our dataset to try and look at the correlation between that. If you wanted to do that, you could of course go that route. However, there's a much faster and more efficient way to look at the correlation to do this. So in the very last episode, I mentioned a library called Seaborn that basically builds on top of material plotting library to build better graphs. And in this episode, we're going to use some of their functions to help us out. So Seaborn has a function called pairplot that actually looks at every single variable in the dataset and plots every possible graph between two variables. Let's actually use this function now to see what it does. So the first thing I'm going to do is actually import the Seaborn library. I'm going to say import Seaborn, and then I'm going to import it as SNS, as SNS is typically the abbreviation you'll see used for Seaborn in code. Then all we're going to do is just type sns.pairplots, and then we're going to pass in our data set. So if we run this, it'll take a minute to actually print it out because it's looking at every single variable and every single row, so the overhead computing is quite high. I'll go ahead and fast forward this here so you don't need to wait for all this to load. And voila, we now have a huge grid of graphs. It might just look like a blob of dots right now, but here's how this pairplot function actually works. So basically what it does is it plots every single variable once on the y-axis. So if you see here, we have on this y-axis here, we have talent, infrastructure, operating environment, research, and so forth. And then it also plots it once on the x-axis, so down here as well. So we have talent, infrastructure, operating environment, and so on. So what it does is it pairs every single variable up until every variable has been paired with something else. So basically there is a graph in here that'll have, let's say, talent on the y-axis and research on the x-axis. Just like there's one that would have research on the y-axis and talent on the x-axis, there's one that would have, let's say, development on the y-axis and total score on the x-axis. So it's basically every possible combination of two variables on this graph. So if, for instance, we need to look at the correlation between operating environment and research, we would find the operating environment on one of the axes, so we could look at this y-axis here, and then we would find where it intersects with research on the other axis. So let's actually scroll down here. Looks like research is this fourth column here. So if we scroll back up, it looks like this graph right here is a correlation between operating environment and research. So because operating environment is on our y-axis, that means it'll be our dependent variable, and because research is on our x-axis for this one, that would be our independent variable. So because of the way this pairplot function actually works, each combination of two variables has a mirrored graph where the axes are just flipped. So if there is a graph where operating environment is the y-axis and research is the x-axis, there also exists a graph where operating environment is the x-axis and research is the y-axis. So for example, look at like these two graphs here across this diagonal. If you look here, you can actually see that these are actually two perfectly mirrored graphs of each other because they actually involve the exact same variables. They're just kind of on the flipped axes. In the same way, if you look at these two graphs here, these are also mirrored because this one has research on the y-axis and then operating environment on the x-axis, whereas this one right across from it diagonally has operating environment on the y-axis and then it has research on the x-axis. So now, what are we actually looking for when looking for a strong correlation? The most common case of correlation is going to be a linear correlation, as this is common and easy to identify. So all that we look for in a linear correlation is a diagonal trend upward or downward. An upward diagonal trend would suggest a positive correlation, while a downward diagonal trend would suggest a negative correlation. Positive just means that the two variables move together, while negative just means the two variables move opposite of each other. So in this grid, most of these variables have some degree of correlation, whether very strong or very weak. So real quick, let's take a look at our grid and see if there's any graphs that stand out as having a somewhat tight diagonal linear correlation. If we look, for instance, let's see, one that sticks out to me right away is this one right here. It looks like with the research on the y-axis and it's talent on the x-axis. So it's this graph right here. This one looks to be like it's pretty nicely correlated. Let's go, okay, total score and talent also seems to be a very good one, where it follows kind of a nice upward diagonal trend. And then another one, which looks maybe even better than that one, is the one that has total score on the y-axis and research on the x-axis. This one actually does look pretty good too. It looks like it's a very tight diagonal correlation there. So why do all these three graphs really stand out to me? If I were to place a perfectly straight diagonal line starting somewhere near the bottom left of the graph and it went perfectly to the top right, many of the data points would fall around that line. So if we go up, like let's say between research and talent, for instance, this graph here, what this means is that generally as the research score goes higher, the talent score tends to go higher as well. In the same way, as the research score goes lower, the talent score tends to go lower as well. Because the variables tend to move together, we would say research and talent are positively correlated. And then the other ones where you found kind of a tight diagonal was, for instance, this total score and this talent one here. This one represents the same positive correlation, meaning total score and talent tend to move very much together. And then, however, it looks like the strongest correlation that we can actually find in this whole grid comes from this graph here that I'm looking at, with total score on the y-axis and research on the x-axis. This graph has data points that follow a far tighter pattern than any other graph on this list, and it appears that total score and research have an incredibly strong correlation. And not only are almost all data points in the lower ranges tightly clumped together, almost one to one, but also if we look at these two outlying dots here in the higher ranges, they look like they're actually still quite in line with the diagonal produced by the lower ranges, meaning that if I made a line here with these lower ranges, and I made a diagonal to kind of go in the middle of all of them, that if it actually kept going, it looks like these two dots would actually be fairly in line with that. Just so we can see this a little bit better, let's use what we learned about material plotting library to further explore this correlation. So I'm going to make a new code block down here, and I'm going to make a scatter plot to actually explore this. So I'm going to type plt.scatter, and then we're just going to pass in the columns of total score and research to make this graph by itself. And remember, we always want the x variable to be first. And so this graph here, we have research as the x-axis variable. So I'm going to pass in dataset research, and then separate by commas to pass in the columns argument. So I'll say dataset total score like this. And then, then I'll actually add plt.show to the bottom of this. And then if we run it, we've now recreated this exact total score and research graph by itself. So this graph here is perfectly identical to this graph here. Obviously, we're just doing this one individually though. And like normal, let's make some quick labels just so we can be a little bit neater about this. Let's say plt.xlabel, or call it research. Then we'll do plt.ylabel, call that total score. And then we'll do plt.title, and then we'll just say total score versus research, like that. And then we'll just run it to have a nicer formatted graph. So now you should have a better idea of what this graph looks like up close. If I were to place a line on this graph to follow the general trend of the data points, we could probably get a very accurate linear correlation between these two variables. Meaning if I had a line starting somewhere in this area and I went all the way perfectly diagonal, all these points would fall somewhat around that line. So the real question is though, how do we actually find that line? Or more importantly, how do we find the mathematical equation for the line given our data points? We'll explore that in our very next episode, where we cover predictive analysis with things like linear regressions that are meant to help us find these prediction values. In this video, you learned how to use all the mean, median, variance, and standard deviation functions, as well as finding the correlation between two variables easily using the pairplot function from Seaborn. And as promised, in the next one, we'll look at finding trend lines for linear correlations and further explore the idea of data prediction. I'll see you in the next one.